Welcome to a detailed exploration of one of ancient Rome's greatest engineering achievements, Opus Caementicium, the revolutionary concrete that helped build and sustain the Roman Empire for centuries, and whose secrets continue to fascinate scientists and engineers today. Unlike modern concrete that often lasts only 50 to 100 years before significant deterioration sets in, Roman concrete has endured for over 2,000 years in some of the most demanding environments on Earth. Structures built with it still stand today across Europe, North Africa, and the Middle East, challenging our assumptions about material longevity, construction techniques, and the very nature of durability in the built environment. This is not myth or exaggeration. It is the real, documented history of a material that transformed the ancient world and whose principles are now being re-examined for the challenges of our own time. The Romans did not invent concrete from nothing. Earlier civilizations in the Mediterranean had experimented with lime-based mortars, but the Romans perfected the formula through systematic observation, experimentation, and large-scale application. By the 3rd and 2nd centuries BC, during the late Republic, they had developed a true hydraulic cement capable of setting and hardening even underwater. The breakthrough came with the incorporation of pozzolana, a volcanic ash sourced primarily from the region around Pozzuoli near Naples in the Bay of Naples, although similar reactive volcanic materials were identified and used in other parts of Italy and the Empire. When mixed with lime and aggregates, this ash triggered a powerful pozzolanic reaction. The silica and alumina naturally present in the volcanic material reacted chemically with calcium hydroxide produced by the slaking of lime, forming durable calcium aluminum silicate hydrate compounds. These compounds created a dense, interlocking matrix that gave the concrete its exceptional strength, water resistance, and long-term durability. Our most important ancient written source on this material is the Roman architect and engineer Vitruvius. In his 10-volume treatise De Architectura, written around 25 BC during the reign of Augustus, Vitruvius provided precise instructions for concrete preparation that reflect generations of accumulated practical knowledge. For general structural work in buildings, he recommended a ratio of 1 part lime to 3 parts pozzolana. For underwater applications such as harbors, breakwaters, and piers, he specified a richer mixture of 1 part lime to 2 parts pozzolana to ensure greater resistance to the erosive forces of seawater. Vitruvius was careful to distinguish between tough fragments of brick or tile and rubble salvaged from earlier constructions. This mixture was placed into wooden formwork or molds and compacted layer by layer using tamping tools to remove air pockets and ensure maximum density. The technique allowed for rapid, economical construction on a scale that traditional cut stone or brick masonry could never have achieved, while also enabling more complex architectural forms such as vaults, domes, and large open interior spaces. One of the most remarkable properties of Roman concrete, observed for centuries but only mechanistically understood in recent decades, is its ability to resist cracking and even self-repair over extremely long periods. In 2023, an international team of researchers from MIT, Harvard University, and institutions in Italy and Switzerland published groundbreaking findings in the journal Science Advances, analyzing samples taken from ancient Roman sites, including Privernum. They discovered that the concrete contained macroscopic lime clasts, chunks of unreacted or only partially reacted lime that had previously been dismissed by modern observers as evidence of imperfect mixing. These lime clasts were formed through a deliberate hot mixing process in which quicklime was combined with the other components at elevated temperatures. This created a brittle high surface area nanoparticulate structure within the clasts. When microcracks later formed due to structural stress, seismic activity, or environmental wear and water seeped into those cracks, the lime clasts dissolved and reacted to precipitate new calcium-rich mineral phases. These new minerals effectively filled and sealed the cracks from the inside, restoring the material's integrity without any external maintenance. This intrinsic self-healing mechanism explains why so many Roman concrete structures have survived earthquakes, centuries of weathering, repeated flooding, and constant exposure to seawater for more than 2 millennia. The Romans applied this extraordinary material across every corner of their empire with impressive results. Perhaps the most iconic surviving example is the Pantheon in Rome, rebuilt under Emperor Hadrian around 120 AD. Its unreinforced concrete dome, with a diameter of 43.3 meters and rising to the same height at the central oculus, remained the largest dome of its kind in the world for over 1,300 years. The Romans achieved this feat by using progressively lighter aggregates, such as pumice, toward the top of the dome, thereby reducing weight while maintaining structural strength. The thick walls incorporated pozzolanic mortar to distribute loads efficiently, and the entire building has withstood multiple major earthquakes and environmental stresses with remarkably little degradation. The Pantheon stands today as living proof of Roman mastery of both material science and structural engineering. Aqueduct systems provide another spectacular testament to the capabilities of Opus Caementicium. The empire constructed more than 1,000 kilometers of aqueducts to supply fresh water to its cities. Rome itself was served by 11 major aqueduct lines that together delivered up to 1 million cubic meters of water every day. Concrete was used to create watertight channel linings that resisted erosion and to build strong supporting piers and vaults over long distances and difficult terrain. The Pont du Gard in southern France, constructed in the 1st century AD, combines stone arches with concrete elements and remains one of the most impressive surviving examples. Similar techniques appear in the Aqueduct of Segovia in Spain and in numerous other provincial aqueducts. These systems relied on precise gradients for gravity-fed flow and on concrete's moldability to form smooth, durable conduits that minimized leakage and sedimentation for centuries. Harbor engineering pushed the material's hydraulic properties to their limit. At Portus, the great artificial harbor built by Emperor Claudius near the mouth of the Tiber River, massive concrete breakwaters and moles were poured directly into the sea inside temporary wooden cofferdams. The chemical reaction between seawater, lime, and pozzolana produced additional crystalline phases such as tobermorite and philipsite that further reinforced the concrete matrix and increased its resistance to chemical attack. Modern scientific analysis of cores extracted from Roman harbor structures throughout the Mediterranean has shown that this concrete not only survived, but often grew stronger over 2,000 years of constant wave action and biological encrustation. In stark contrast, many modern Portland cement structures in similar marine environments begin to degrade within decades due to chloride penetration and corrosion of steel reinforcement. Concrete also formed the backbone of the famous Roman road network that linked the empire together. The Appian Way and other major VIA featured foundations of compacted rubble bound with pozzolanic mortar, topped with durable paving stones. This layered construction provided stability even on soft soils and withstood the heavy traffic of legions, merchants, and imperial messengers for centuries. In cities throughout the provinces, concrete enabled the rapid construction of forums, basilicas, public baths, and amphitheaters. The Colosseum, completed in 80 AD under Emperor Titus, used extensive Opus Caementicium in its substructures and vaults to support an elliptical arena that could seat up to 50,000 spectators. After the Great Fire of Rome in 64 AD, Emperor Nero's building codes encouraged the widespread use of brick-faced concrete, which accelerated urban rebuilding and produced more fire-resistant structures across the capital. The widespread adoption of Opus Caementicium had profound economic and social consequences. It dramatically reduced reliance on highly skilled stonemasons for every element of construction, allowing faster project completion with semi-skilled labor and locally available materials wherever possible. Pozzolana deposits near Rome and the Bay of Naples provided a readily available resource, while the empire's extensive trade networks distributed similar volcanic materials from other regions when needed. Concrete made possible the large-scale public works funded by imperial patronage or local elites, reinforcing political stability and cultural unity across vast territories. Grand structures such as the Baths of Caracalla and the Baths of Diocletian in Rome demonstrated how concrete could span enormous interior spaces without excessive internal supports, creating impressive public environments for hygiene, recreation, and social interaction. Regional variations in concrete formulation further highlight Roman adaptability and pragmatism. In areas where natural pozzolana was scarce, builders substituted crushed terracotta or other reactive ceramics to create what modern researchers sometimes call artificial pozzolans. In North Africa, the Levant, and Britain, local volcanic or sedimentary materials were tested and incorporated wherever they exhibited suitable reactivity. This flexible approach ensured that concrete technology could spread throughout the empire without total dependence on Italian supplies. In Britain, for example, concrete was adapted to cooler and wetter climates and used effectively in bathhouses and military fortifications. Despite its remarkable success, the large-scale production and use of high-quality Roman-style concrete gradually declined after the fall of the Western Roman Empire in the 5th century AD. The reasons were practical and systemic, rather than the result of any sudden or mysterious loss of knowledge. The fragmentation of the empire disrupted centralized production, long-distance supply chains for premium pozzolana, specialized training programs for builders, and the funding of massive imperial building projects. In the late antique and early medieval periods, resources shifted toward repair, fortification, and simpler construction methods using locally available stone or non-hydraulic lime mortars. While Vitruvius's treatise survived and continued to be studied, the full combination of raw materials, hot mixing techniques, and workshop traditions that had been refined over centuries became far less common in Western Europe. In the Byzantine East, some Roman building practices persisted in more limited forms, but the golden age of Opus Caementicium had passed. It was not until the 19th century that modern Portland cement was developed and patented by Joseph Aspdin in England in 1824. Portland cement offered advantages in production speed, consistency, and suitability for industrial-scale building. However, it generally lacks the long-term durability of Roman concrete in harsh environments because it does not form the same self-reinforcing crystalline structures or self-healing capabilities. Modern concrete typically requires steel reinforcement, which can corrode over time, causing spalling and structural weakening within decades under certain conditions. In contrast, Roman concrete's ongoing pozzolanic reactions and built-in lime-classed reservoirs allowed it to improve with age, especially in marine settings. Scientific interest in Roman concrete has intensified in recent decades, driven by both historical curiosity and urgent practical concerns about sustainability and infrastructure resilience. The 2023 discovery of the self-healing mechanism has inspired laboratory experiments to recreate Roman-inspired mixes today. By incorporating controlled amounts of quicklime and applying hot mixing techniques, contemporary researchers have produced samples that demonstrate crack-healing capabilities similar to the ancient material. These findings suggest promising applications for modern infrastructure, where longer-lasting concrete could dramatically reduce maintenance costs and the enormous environmental footprint of cement production, which currently accounts for a significant percentage of global carbon dioxide emissions. Roman methods, which rely on lower temperature lime production and natural pozzolans, offer models for lower carbon alternatives, although scaling them globally presents challenges related to the availability of suitable volcanic ash deposits. The legacy of Opus Caementicium extends far beyond mere historical interest. It embodies the Roman approach to engineering, pragmatic, adaptive, and deeply rooted in a practical understanding of natural materials and their chemical interactions. From the precise specifications recorded by Vitruvius to the empirical successes visible in surviving monuments like the Pantheon, the Pont du Gard, and the harbors of Portus, Roman concrete illustrates how careful observation, experimentation, and resourcefulness can produce innovations that outlast empires. These structures continue to stand not only as architectural marvels, but as powerful reminders of what is possible when builders align their techniques with the chemistry of the earth itself. As we confront the limitations of contemporary building materials in an era of climate change, resource scarcity, and aging infrastructure, the study of Roman concrete offers valuable lessons. It demonstrates that durability need not always be sacrificed for speed or cost, and that ancient wisdom, when examined through the lens of modern science, can inform more resilient and sustainable practices for the future. The pozzolanic reaction, the role of lime clasts, the synergy with seawater, these elements combined to create a concrete that defied expectations of decay and that continues to reveal new secrets more than 2,000 years after it was first mixed. This is the real story of Rome's engineering achievement, grounded entirely in archaeological evidence, surviving ancient texts, and peer-reviewed scientific research. No speculation, no conspiracy, no exaggeration. The concrete that once supported legions, emperors, and the daily life of millions now supports scientific inquiry and offers practical inspiration for the challenges of our own century. The Romans left us more than ruins. They left a blueprint for building wisely, one that respects both human ambition and the enduring forces of nature. The material that helped Rome rise to greatness continues to teach us today, reminding every new generation that true innovation often lies in understanding and refining what has already proven its worth across the centuries.